Hello everyone, and welcome back to our series on algorithms. In this video, we will depart from our previous discussion on graph algorithms to talk about branch and bound algorithms. If you enjoyed this lecture, be sure to like, comment, and subscribe. With that, let's begin. Unlike all of the previous algorithms that we have discussed, branch and bound algorithms are not typically used to solve problems that fall in the complexity class P. In other words, problems that can be solved in polynomial time. Rather, these algorithms are used to provide practical optimizations that can radically improve runtime over naive approaches. The basic premise of branch and bound algorithms is as follows. Suppose we represent our NP problem as a decision tree where we want to maximize a given function f, which maps the leaves of the tree to real values. We can then define a function h such that the output of h for any node t upper bounds the value of f for all of the leaves L which descend from t. Using this function, we can predict when traversing further from a given node is guaranteed to not give a more optimal solution than a given solution we have found in a different part of the tree, meaning that we can truncate the tree at this point. In general, the algorithm for a branch and bound problem proceeds as follows. First, we define the problem as a maximization of f, which maps the leaves of a tree to some real output. Define the current maximum m to be negative infinity, and the node x corresponding to this maximum to be null. Starting from the root of the tree, traverse the nodes in pre-order via DFS. At each node t, if t is not a leaf, compute h of t. If h of t is less than m, end traversal of this branch early. If t is a leaf, check if f of t is greater than m. If this is the case, set x equal to t and m equal to f of t. Once traversal completes, return x. The correctness of this algorithm follows trivially from the fact that since f of L is less than or equal to h of t for all leaves L with ancestor t, if h of t is less than m, then f of L must also be less than m, meaning that the leaves cannot contain an optimal solution. Let's look at some examples of how branch and bound can be used to solve some NP problems. Let's revisit a problem we've talked about multiple times before, the 0-1 knapsack problem. As a quick refresher, the knapsack problem has us find a subset of n items which maximizes the total value of the items while still remaining below a given weight or capacity constraint. In our dynamic programming video, we talked about how to solve this problem efficiently when the weight constraint W is significantly less than 2 to the n. Rephrasing this problem as an n-level decision problem, we have that layer I corresponds to a decision over whether or not to include item I. Each node can be represented using a bit string, where a 0 corresponds to an item not being present, and a 1 corresponds to an item being present. For our purposes, we will define the left child as a node which includes I, and the right child as the node which does not include I. The naive approach to this problem would be to iterate over all the 2 to the n leaves and identify the subset which maximizes the total value whilst respecting the weight constraint. However, we can do better using branch and bound. In particular, we define our function f that we want to maximize to simply be the total value of the knapsack represented by each leaf. For our upper bound on f, we have several different choices. For this case, we will choose h to be the value of the current knapsack plus the remaining space in the knapsack times the value over weight of the item with the highest value over weight ratio not in the knapsack already. Of course, this is assuming that there is space left in the knapsack and that the capacity constraint is obeyed. So if this condition does not hold, then we will simply set this to be 0. The correctness of these upper bounds stems from a relaxation of the 0-1 knapsack problem known as the fractional knapsack problem, which we discussed in a previous video on greedy algorithms. To make this bound as tight as possible, we will process these items in the decision tree in order of decreasing value over weight, as we would for the fractional knapsack problem. Consider the following example of a knapsack problem where we have 5 items with values 7, 6, 3, 4, 1, and weights 10, 9, 5, 7, 2, with a maximum weight constraint of 18. Note that I have sorted these items in order of decreasing value to weight ratio. If we now apply the branch and bound method, we can see that we get the maximum value possible to be 11. The node corresponding to the maximum in a run-through corresponds to the bit string 10101, meaning that this knapsack contains items 1, 3, and 5. With the naive approach, we would have had to traverse the full decision tree consisting of 63 nodes. However, by employing branch and bound, we only needed to traverse 19 nodes, meaning that we effectively trimmed off 70% of the tree. Hence, using branch and bound, we can effectively solve the knapsack problem potentially in much faster time than the naive solution. However, note that truncation is not always guaranteed in this algorithm. Hence, in the worst case, this algorithm is still only as efficient as the naive routine, meaning that the worst case time complexity is still O of 2 to the n. Nevertheless, this method provides a practical advantage over the naive method on average. Let's look at another famous NP-complete problem, the traveling salesman problem. The TSP asks us to find the lowest weight Hamiltonian cycle for a given graph. In other words, we must find the lowest weight cycle that visits every vertex once and starts and ends from the same vertex. The physical interpretation of this problem is that vertices correspond to cities and edges to distances between cities. And our goal is basically to figure out the shortest path that visits every city once and returns back to the original city. Like the 0-1 knapsack problem, this problem can also be solved using dynamic programming. However, let's look at how branch and bound can be used to solve it. We can formulate this problem as a tree by having each node at level k correspond to a given path v1 through vk, and having its children represent the path v1 through vk to vk plus 1, such that vk plus 1 is not equal to any of the previous vertices, and vk, vk plus 1 is an edge in the graph. We can then define a function f which computes the total weight of the given cycle at each of the leaves. Note that this problem is actually a minimization problem rather than a maximization one, meaning that our function h that we want to find should actually be a lower bound in this case. The natural question, of course, is how one would even bound f. Well, consider this. For every vertex in a cycle, there exists exactly 2 edges in the cycle with endpoints at this vertex. Hence, if we only know part of a cycle, we can lower bound the total weight of the remaining part of the cycle by simply summing together the 2 lowest weight edges connecting to each vertex, not yet included in the cycle. We then also add the lowest weight edge for the 2 endpoints of the existing path. However, since this effectively double counts the edges in the cycle, we then have this entire quantity. Hence, we have the following definition of h. Using the general branch and bound algorithm with these definitions, whilst altering the conditions appropriately for minimization, we can therefore calculate the lowest weight Hamiltonian cycle faster than we would be able to with a naive method on average. Again, however, pruning of the tree is not guaranteed, meaning that we could still have to traverse every single node. Hence, the complexity is still the same as that of the naive method, which is simply to check all n-1 factorial permutations of vertices, assuming that we fix the starting vertex. Since we then have to sum over the weights of the n edges of each cycle, we have that the total complexity is O of n factorial. Nevertheless, this method is generally much faster than the naive method for all practical purposes. This concludes our brief foray into branch and bound algorithms. All in all, we discussed how branch and bound techniques can be used to perform practical optimizations for solving NP-hard problems. In the next video, we will move in a completely novel direction and talk about solving optimization problems via linear programming. I hope you enjoyed this video, and I will see you next time.